we want to define a new concept which is inverse of a number x. And here inverse of a number x is some y such that x times y is congruent to 1 mod r. So it means that if I want to use like definition of mod and congruence classes, congruent numbers, I can say that xy, or there exists k such that xr minus kr is equal to 1. Or I can, like if I want to use predicate logic, I can say there exists y and there exists k such that xy minus kr is equal to 1. So to understand this concept better, if I have 5 and I have the number 6, that y or inverse of 5 is 11, or let's say inverse of 5 mod 6 is 11, because 5 times 11 mod 6 is equal to 1. Or in the other words, 5 times 11 is equal to 55, and if I divide 55 by 6, then the result is 1. We can see, if you test, you can see that we cannot find something like 4 is congruent to 1 modulo 6, or 6 is not congruent to 1 modulo 4, and there doesn't exist any inverse for 4 or 6 with the mod of the other one. And you can find out that it is actually related to the example that we have in the previous lecture, but we want to have 2 more concepts, and we are going to see one theorem based on the definition of inverse. The first definition is about relatively prime numbers. We call 2 numbers a and b relatively prime if they don't have any common divisor, or there is no c greater than 1 such that c divides a and b both. So we call a and b relatively prime if they don't have any common factor or let's say it is not true that there exists c such that c is greater than 1 and c divides a and c divides b. If you remember, d of c and a means that c divides a, d of c and b is c divides b. So there doesn't exist such that c. Now that their common factor is 1, and actually that 1 is, since it is not prime, is not composite, we can say they don't have any common factor. We call those 2 numbers a and b relatively prime. The other concept I want to talk about is about greatest common divisor. Actually, it is the biggest c that I can find, such that d of c and a and d of c and b. The biggest c such that this, and we can write it as GCD of a and b. So if GCD of a and b is equal to 1, it means that the greatest common divisor of these two numbers is 1, and actually it means that they are relatively prime to each other. Another concept that we can talk about is least common multiple, or LCM. And LCM of A and B is the number C, the smallest c, such that D of A and C and D of B and C, which means A divides C and B divides C. Can I write them like in a better way? Instead of biggest, I can rewrite that as max C such that C divides A and C divides B, and here instead of a smallest c, I can say mean C. The theorem that I want to mention now, and we are going to show how we can prove that and show that, is the inverse theorem. Inverse theorem says natural number A has inverse mod M if and only if A and M are relatively prime. So if you remember, we had that example at the beginning that 5 has that inverse mod 6 and that inverse is 11, but I cannot find inverse for 4 mod 6. We see that 5 and 6 are relatively prime, but 4 and 6 are not relatively prime. In the next video, we are going to learn about Euclidean algorithm and actually how to prove inverse theorem. Okay, before starting to talk about Euclidean algorithm, I want to tell you what actually we want to do. We want to learn about Euclidean algorithm, which takes two numbers, two naturals as input, and give us GCD of them. So we take A, B, and by Euclidean algorithm, we find some number which is GCD, or greatest common divisor of A and B. Then we prove that actually Euclidean algorithm is giving us GCD, and what we compute here is the GCD of A and B. Then we show that we can write GCD of A and B, or let's say we can give any letter for that, C, as a linear combination of A and B. So I can rewrite it as, for example, AK plus BT. And then we want to show that for some A and B, if A and B are relatively prime, so GCD of them is 1. So if A and B are relatively prime, GCD of A and B is equal to 1, so that C is equal to 1. So I can write 1 as AK plus BT when A and B are prime to each other. Now, if I can write 1 as AK plus BT, it means that A has inverse mod B. So by doing all these, I want to show that if two numbers are relatively prime, then A has inverse mod B. And also I can write like B has inverse mod A. So it is the path we want to follow in this video. I want to teach Euclidean algorithm here, and I want to use an example to do that. So let's assume I have two numbers, A0 and A1, which are those two like first numbers, A and B, that I want to compute GCD for them. And I give these numbers 72 and 46 here. So in the first step, I compute 72 mod 46. Or actually, I divide 72 over 46 and find the remainder, which is 26. Now I give this 26 a new name, A2, in my sequence, and it is 26. Now, in each step, I follow the same way, using the last two A's that I have, AI's that I have. So now I compute remainder when I have 46 over 26, which is 20. So I store that as 20. Next, 26 mod 20, which is 6. So A4 is 6. Next, 20 mod 6, which is, so if I divide that, it will be 3 times 6, which is 18, and it is equal to 2. A5 is 2, and finally 6 mod 2, which is equal to 0, and I have A6 as 0. When I reach to the index such that that index is equal to 0, I go to the level before that, and I can say this one is GCD of 72 and 46. Okay, how can I show that? Actually, what happens here is that, let's assume that I have a number. First of all, I see that 2 divides 72 and divides 46. I'm good with that. I mean, I can prove that 2 is a divisor of 72 and 46 both. Now, let's assume that I have x such that x divides 72 and x divides 46. I know when something divides two numbers, then it must divide the subtraction of those. So x must divide 26 and x must divide 20, because it divides 46, it divides 26, so it must divide 20. And then it must divide 6. And since it divides 6, I can say that since it divides 20 and it divides 6, so also it divides 18, because it divides 6, so it divides 3 times 6. And then I can subtract these two and say x must divide 2. X must divide 2, so I know that this number that I'm talking about divides 2, so it is less than equal to. So I can realize that the number, the arbitrary number that I'm talking about, for sure it's less than equal to 2. And since I know 2 is a common divisor of 72 and 46, then it must be the greatest common divisor of these two. Okay, now I want to change the way that I wrote this and write it in this way. I can write 72 as 1 times 46 plus 26. 46 is equal to 1 times 26 plus 20. 26 is 1 times 20 plus 6. And 20 is 3 times 6 plus 2. And finally 6 is equal to 3 times 2 plus 0. Okay, I can rewrite them like this. Now what I want to do is that I want to write each of these in the way of a linear combination of 72 and 46. Let's see what will happen. So I can write 72 as 1 times 72 plus 0 times 46. I can write 46 as 0 times 72. If these dots doesn't mean that precision, it means that multiplication, plus 1 times 46. Next, I want to write 26, which is subtraction of these two, and then I know it is like this, 72 minus 46. So I can say it is 1 times 72 minus 1 times 46. And then for 20, which is subtraction of these two, I can write it as this minus this, which is negative 1 times 72. This minus this, which is plus 2 times 46. And then subtraction of 26 and 20 is 6, and I can write it as 1 minus minus 1, which is 2 times 72, negative 1 minus 2, which is negative 3, times 46. And then I know 20 is not, like after that I have like 20 minus 3 times 6. So when I want to have like 2, it is like I do this. So 2 will be negative 1 minus 6 of them, which is minus 7 times 72, and 2 minus negative 9, which is plus 11 times 46. And just to make sure we can test that, so 7 times 72 means that 490, 504, and 11 times 46 will be equal to 506. So negative 504 plus 506 is equal to, and it is correct. So I just wanted to test if I did that correct. Okay, now I have this, and now actually I showed that I can write the GCD of 72 and 46 as a linear combination of 72 and 46. Now I want to show that if GCD of two numbers is equal to 1, I can do the same as write 1 as a linear combination of those two. And then actually it means that I have that inverse. To use two numbers with GCD 1 and showing the inverse theorem, I chose these two numbers, A72 and B47. First of all, I need to show that their GCD is equal to 1. And how can I show that? By using Euclidean algorithm. So first of all, 72 mod 47 is equal to 25. 47 mod 25 is equal to 22. 25 mod 22 is equal to 3. And 22 mod 3 is equal to 1. And finally, 3 mod 1 is equal to 0. We know that not the step that we reached to the 0, but the one before that is the GCD we have. So GCD of 72 and 47 is equal to 1. Now I want to follow what we did for 72 and 46 and write it in the linear combination forms of 72 and 47. Well, 72 is equal to 1 times 72 plus 0 times 47, and then I go to 47, which is 0 times 72 and 1 times 47. Subtraction of these two will give me this minus this, which is 1 times 72, 0 minus 1 times 47, and here subtraction of these two will give me negative 1 times 72, and 1 minus minus 1, which is plus 2 times 47. The subtraction of these two, 25 and 22, will give me 3 with 1 minus minus 1, which is 2, and minus 1 minus 2, which is minus 3. In the next step that I want to reach that 1, actually I need to see that 22 actually minus 7 times 3 will be equal to 1. So I need to multiply that 7 to both parts of my equation or linear combination. And it will be negative 1 minus 14, which is negative 15 times 72, and 2 plus 21, which is 23 times 47. Okay, now I have 1 and I can write it as combination of 72 and 47. What it gives me is that 72 has inverse and 47 has inverse. What is inverse of 47? See, 47 times 23 has, when I divide this by 72, I get 1. So it has inverse, and inverse of 47 mod 72 is 23, and negative 15 is actually inverse of 72 mod 47. And actually when I say inverse is negative 15, when I'm in mod 47, it actually means that I can subtract that from 47 and I can say that 32 is inverse of 72. You can compute that and see that if we multiply 32 times 72 and subtract 1 from that, then over 47 it will be, the remainder will be 0. Okay, so having that, actually we can, by this actually we proved inverse theorem. Euclidean algorithm is not efficient when we want to work with hand and we have like really big numbers, but it is really efficient when we want to use that with computers. So Euclidean algorithm is one thing that we actually use. But the algorithms that we had so far, like Eratosthenes, or the one for finding like prime factorization, is none of them actually are really efficient with computers as well. So, and we are not going to actually talk about some better algorithms about finding prime numbers or deciding if a number is prime or not. Okay, we are done with that. In the next lecture, we are going to talk about Chinese remainder theorem, and we'll see you in the next lecture. Thank you.